Good morning, everyone. In this video, our group is presenting the paper Archer Training Language Model Agents via Architecture Multiple RL. This paper studies how deep reinforcement learning can train large language models as multi-turn decision-making agents instead of only single response test generators. I will introduce the research background and the research problem. The background is a result LLM based on agents. Model LLMs can answer questions, write codes, use tools, and interact with users. However, when an LLM becomes an agent, the task is no longer just generating a suitable answer. It needs to make decisions, observe feedbacks, and adjust its next action based on the previous interaction. This creates the main research problem. Most existing LLM reinforcement learning methods focus on single-turn reward maximization. For example, in RLHF, the model usually receives one prompt, generates one response, and is optimized using a reward for preference single. This is useful for chatbot element, but not enough for agentic tasks. In real agent tasks, the model may need to gather information, take intermediate actions, and only receive the final reward later. Therefore, the authors ask, how can we design an effective and efficient LLM method for LLM agents over multi-turns? To answer this, the paper proposes Archer hierarchical active framework. Next, King Hong will explain the key RL challenges behind the problem.
For current challenges, as Fayang mentioned, the problem is no longer simple text generation. The paper treats multi-turn language agent task as a reinforcement learning problem. In IL terms, the step is the interaction history between the LLM and the environment. The action is the language output or tool action generated by model. Lastly, the reward measure whether the agent is moving toward task successful. This makes LLM training similar to a macro decision process, but with language as the action space. There are three main challenges. The first is delay reward. In many agent tasks, the model does not immediately know whether an action is good because the reward may only appear after several turns. The second is credit assignment. If agent fails after many turns, the model must learn which earlier decision caused the failure. The third is the sample efficiency. Multi-turn RL may require interaction with human, web server, or tools, which can be slow and expensive. On policy methods, such PPO need new samples from the current policy, so they cannot reuse all data efficiency. There are also a language-specific challenge. If each token is treated as one action, the RL horizon becomes too long because the final reward must be propagated backward across many token decisions. However, one full trace is treated as one action, the action space becomes too large because there are too many possible sentences or two commands. To balance these two problems, the paper proposed Archer. The main idea is to train the LLM agent using two reinforcement learning level, the utterance level and the token level. Now I pass to Ziling for further methodology discussion.
After Ken Hong introduced the reason of using Archer, I will explain how the two levels work. At the utterance level, Archer treats a complete utterance as an action. This utterance can be a natural language response or a to-command. The high-level critic evaluates whether this full utterance is useful for long-term task success. In this paper, the critic learns a Q function and a value function. First, the Q model objective uses a Bellman-style target, current reward plus discounted future value. This is important because the agent should not only choose actions that look good immediately, but actions that help the whole task succeed later. This paper describes this as Bellman consistency between the Q model and the target value model. Next, the V model objective trains the value model to approximate the expected Q value of actions sampled from the current policy. This allows the framework to estimate how good a state is under the current LLM actor. At the token level, the actor is trained using a policy gradient method. Instead of using a normal single return reward model, it uses the advantage value derived from the utterance level critic. This means the token generator is guided by a long-term task value, not only by whether the next token looks likely. This paper also mentioned an optional token level baseline value function. This is used to reduce the variance of policy gradient learning, especially when actions are long and diverse. Next, Jason will explain how this framework is implemented in the experiment.
Okay. Hello everyone, I'm Jason. I will now explain the implementation and experimental setup. Archer is designed for multi-turn LLM agent, where decision must consider long-term outcome rather than just the next token. To achieve this, it uses a hierarchical reinforcement learning structure. At the high level, a critique will each generate outcomes using temporary different learning, which combine the current reward with an estimate of future value. Archer also store previous interaction in a replay buffer to reuse. At the low level, the actor is the language model itself, generating tokens step by step. The critique advantage estimate is then used to update the policy. Okay, to evaluate the method, the actors test Archer on several multi-turn environments. This includes detective game, a test-based mystery game, 20 questions, and a smaller subset version. Guess My City, where the agent asks open-end questions, and Workshop, a task where the agent buy items from an online store. This environment tests different capabilities such as planning, information syncing, dialogue interaction, and tool use. The paper compared Archer with server baseline approach. This includes TPO, a widely used on-policy reinforcement learning method, filter behavior cloning, which is an imitation learning baseline, and CHI, an alternate level offline reinforcement learning method. That's all for my talk. Next, Robert will discuss the result and evaluation.
Now I will discuss the experimental result and critically evaluate the paper. First, please look at the figure 3. It compares Archer with PPO, CSAI, and filtered behavior cloning across 4 online RL tasks. Overall, Archer improves steadily as more trajectories are collected. It outperforms other methods on 3 tasks and matches the baseline on the simpler detective game task. The most important result is sample efficiency. In 20 questions, PPO needs more than 100,000 samples to reach an average return just above -17, while Archer reaches this level with fewer than 1,000 samples. This shows around 100 times better sample efficiency, which is important because online interaction with humans, tool, or web servers can be expensive. Next, figure 4 shows the web shop result. This is very interesting because Archer fine-tunes a smaller GPT-2 based model, but it still outperforms CSAI, filtered BC, and GPT 3.5 prompting baseline in this control webshop benchmark. This suggests that proper reinforcement learning training can be sometimes useful than relying only on a larger model with prompting. For the ablation study in figure 5, the replay buffer improves stability while replacing GPT-2 with Mistral 7B helps the engine learn faster. However, the paper still has limitations. When the experiment use small models, the benchmarks are controlled and reward hacking remains possible. Therefore, Archer is very strong but still need more realistic testing. Finally, Howren will conclude with our group insight and significance.
To conclude, our group believes this paper is significant because it shows a direction for training LLMs as real decision-making agents. Many current LLM agent systems rely heavily on prompting. Prompting can guide the model, but it does not directly improve the model's underlying decision policy. Archer is different because it trains the model through reinforcement learning to improve long-term task performance. Our main insight is that the hierarchical design is the most valuable contribution. It is a practical compromise between two difficult choices. Token-level RL is natural for language generation, but the horizon is too long. Utterance-level RL reduces the horizon, but the action space becomes too large. Archer connects both levels using an utterance-level critic and a token-level actor. This is important for future agentic AI, web agents, coding agents, research assistants, and customer support agents, only to plan, observe feedback, and revise actions over multiple steps. These are not only language generation problems, they are reinforcement learning problems. However, future work should focus more on safety, human feedback, and robustness. In real applications, task success alone is not enough. The agent must also be reliable, truthful, and aligned with human intentions. Overall, Archer shows that better LLM agents may come not only from larger model or better prompts, but also from better IL training structures. Thank you.